Well, thank you. It's a pleasure to be here. This conference has grown a bit over the years. I didn't make the first few. In fact, I didn't get in the semiconductor industry, as you just heard, until 1956. And even then, I didn't go to solid-state circuits conferences. Chemists didn't know an awful lot about circuits. But when chemists started making circuits in the early 60s, I did attend several of the conferences. And that time, they were all in Philadelphia. And Philadelphia in February, it was always easy to convince your spouse that it was really hard work, you weren't going on a boondoggle. I'm not quite so sure San Francisco is that easy to sell these days. Well, many of the parameters related to the semiconductor and solid-state circuits industry have shown exponential dependencies over the years. But no physical quantity can continue to change exponentially forever. There's always some kind of a catastrophe if you project it far enough into the future. So what I want to do today is look at some of these exponentials and maybe give some idea where they might go and talk a little bit about how we're going to deal with the looming catastrophes that people seem to be projecting as they look further down the road. The first one I want to look at is the growth of revenues in the industry. This is a phenomenal growth industry. It's grown 80-fold over this 35-year period I've depicted here, a compound annual growth of some 14%, even with the flattening of the last few years. The dips and bumps on this exponential curve may not look so severe. This one perhaps is a little more severe than the rest. But I look back here and realize that in 1974 and again in 1984-85, Intel had to get rid of a third of its workforce. So exponentials tend to kind of distort things that are more nearly experienced linearly when you're actually there. But while this is phenomenal growth, if you want to see the real underlying growth of the industry, look at the output. This is the number of transistors shipped per year, as near as I can estimate it over the same period. And this has grown 8.5 orders of magnitude over that period. 300 million fold. Now that's a growth industry, maintaining an average growth of about 80% per year over this whole time period, and having a significant period, whoops, too many buttons on the mouse, a significant period in here where it actually doubled every year. That is, we had more electronics built in the year than existed at the beginning of that year when we started out. Truly phenomenal growth. I've tried to illustrate this number, getting up toward 10 to the 18th, and I've used raindrops falling on California. E.O. Wilson, the Harvard biologist expert on ants, estimates that the number of ants in the world is between 10 to the 16th and 10 to the 17th. So for years I used that. Now each ant has to carry 10 to 100 transistors if it's going to take care of its load. Perhaps another way of looking at the size of this number, I estimate that the number of printed characters produced every year is between 10 to the 17th and 10 to the 18th. That's all the newspapers, books, magazines, Xerox copies, the computer printouts that you throw away, everything, is the same order of magnitude as the number of transistors that the industry sells. Of course, we print a lot of them we don't sell. Those are the ones with little red dots on it when we get through sorting them. This is phenomenal, and we sell them for about the same price as a printed character in your Sunday New York Times. But the power of the industry is when you divide one of these plots by the other and get the average cost per transistor over this period of time, dropping from about $1 to 0.2 of a microbuck. And that's the average transistor cost during this time period. If you look at DRAMs, it's an order of magnitude below this. You get 50 million transistors for $1 these days. And not only the transistors, you get all that circuit design and interconnections and things thrown in free. It really is a spectacular industry, completely unparalleled by anything else I can see. It's hard to realize when looking at that, that in about 1960, I don't remember the exact date, the industrial engineers at Western Electric, looking at the transistor, estimated that eventually it might cost about 60 cents to build one, looking at time and material studies of the way things were happening at that time. This multiple million-fold reduction in cost requires some really special things in the industry. First of all, it requires a technology that has phenomenal capability. I think a unique technology underlying the industry. And a fantastically elastic market. It has to be able to consume 10 to the 18th transistors a year and growing. And also, in order to make it happen, it has to have the contributions of a lot of people doing circuit design, clever extensions, developing the capability to continue it, and technologists that keep the technology moving rapidly. I go back a bit in time. This is what a transistor looked like about 1959. I didn't have one from 58, which was the first year that transistors were manufactured on a whole wafer, essentially, rather than one by one. But this was a 1-inch wafer back in 1959. A real breakthrough at the time, because one of my first contributions to the industry was proving when you went above 3/4 of an inch in diameter, your yields went to 0, the material was so bad. This shows one of my technical contributions, that flat part on the bottom of the wafer that lets you align it in 2 dimensions. And there were about 200 possible transistors on a wafer like this, and if we were lucky, something like 10% of them were good. Now, of course, we get a lot more microprocessors on a chip, on a wafer, each with millions of transistors, and very, very much better yields. If we take a next step from these early planar transistors to the early planar integrated circuits, this was one of the very first micrologic circuits made. The first integrated circuit was kludged together by Jack Kilby at TI. Fairchild had the planar technology in place, so we had the technology that made these things practical, and Bob Noyce saw how to extend that technology to get to something that would be worthwhile. This was one of the first ones we built. This was a flip-flop consisting of 4 transistors and 6 resistors. It was one of the micrologic family. The die was round, so we could bond it right to the header with little dabs of conductive epoxy. Since the yield on making 6 bonds to a chip was going to be so low, we thought we needed something that didn't detract from the yield from the assembly point of view. It's a terrible picture. I'm sorry that this is what we have left to show those very early days, but maybe it shows a bit about the problems we had. Now, you might think integrated circuits were an obvious solution and were immediately accepted. This was not the case at all. This was a tough sell. Our customer in those days, the technical interface with our customer was typically the circuit designer. We were making transistors and things like that. And to go to the circuit designer and tell him, hey, we're going to do your circuit design for you, it wasn't something that was sold very easily. The reliability people looked at these, and they were used to taking transistors and measuring their parameters over periods of time, looking for drift. And they said, gee, we can't measure the transistors here. You can't get a hold of them. How will we know if it's reliable or not? But I remember going to one aerospace company that said, gee, they used 16 different flip-flops in the circuits, in the systems they built. they could never use a standard flip-flop. They had an expert for each of those, and they really had to be specially designed. And then Bob Noyce made another one of his major contributions to the industry. He said, okay, we'll sell you the circuit for less than you can buy the transistors and resistors to build it yourself. And that was a major breakthrough. The fact that it was also considerably less than it costed to build the integrated circuit at the time was of little consequence. We had to develop a market for them. And of course, the solution the semiconductor industry developed was whenever there's a problem, lower the price. That's the way you solve all of these things. Let the elasticity of the market bail you out. Well, during that time, the early integrated circuit days, I was director of R&D at Fairchild, and had a little bit more visibility than most people did in where integrated circuits were taking us. And I was asked to write a paper for the 35th anniversary issue of Electronics magazine, where I predicted what was going to happen over the next 10 years in the component market, actually semiconductor components. And that's when I plotted this curve that eventually became known as Moore's Law. Extrapolating from about 60 components to 60,000 over 10 years was pretty aggressive. I never expected it to be precise. I was trying to get the message across that this was going to be the cheap way to make electronics, putting a lot of it on a chip, rather than building it up from individual components soldered together. But in fact, it turned out to be more precise than I ever could have imagined. If I put the data on it here, this is what happened, a few of the points over that time period of the most complex circuits available. They fit amazingly well on it, and my friend Carver Mead, professor at Caltech, dubbed this Moore's Law. And what has happened since then? Well, in 1975, I updated it, added the purple line, and I argued why the slope was going to change from doubling every year to doubling every 2 years. My data said it ought to change right then, but the stuff I saw in the laboratory, which was generally CCD memories, suggested that there were a few generations where we were going to continue to double. So I said, oh, we'll double again for the next 5 years, then we'll go to the slope of every 2 years. And CCD memories never quite worked out that way. There was a problem called soft errors that came around. CCDs are much better imaging devices than they are memories. So instead of waiting 5 years to break, the actual data broke at about that time. I got the slope pretty close, but that 5-year hiatus really made it so it didn't fit as well as it might have. This shows what a wafer in the early production days, 3/4 of an inch the size of the nickel, looks like compared with a modern wafer. One of the other things that I projected in 1975, a bit tongue-in-cheek, was what was going to happen to wafer size, again using my semi-log paper to extrapolate. One of my colleagues showed what actually happened. I had remembered I'd only predicted 56 inches, but he went back and got the original data. And not only have things like this have occurred, the structure has gotten complex. If we take a cross-section through a modern process, a modern 7-layer metal process with things like tungsten plugs down here at the bottom, all the interfaces and one thing and another. This is amazing to me. I remember when the principal argument to go from bipolar circuits to MOS circuits was process simplicity. You only needed 5 masks. We've succeeded in driving that up to 25, and I don't know where it's going to stop. This actually it surprises me. One technology that made this possible was the idea of chemical mechanically polishing after each layer, so you maintained a flat surface if you build up insulators and metals and develop the structure. Without that, the topography became so complex that you couldn't get more than 2 or 3 layers of metal before it was unmanageable. The IBM invention of the chem-mechanical processing really allowed this to continue, and I suppose if I plotted the number of metal layers versus time, it would also be close to an exponential, although I haven't plotted it in that direction. Of course, the big driver for the improvements over a period of time has been our ability to make smaller and smaller features. The original planar transistor didn't push that too far, but starting with the early integrated circuits, we've been on a very constant change, or were for many years, of cutting the dimension in half about every 6 years. That's 2 steps, generally 0.7 in a step. So you double the density every 3 years. Every 6 years, then it went down a factor of 4. And of course, I would have expected that to start rolling off. Actually, the opposite has happened. The last few generations, and projected going forward, the time period between generations has stepped down to 2 years rather than the 3 we've done historically. This is amazing to see a curve like this accelerate rather than start to round out. And you see some of the other comparisons you might hear. People always start with the human hair. Well, the human hair is a few orders of magnitude away from where we are now. We're working at AIDS virus sizes and moving on down towards single molecules. I picked a pretty big molecule here. But there's still quite a ways to go before we get to that point. Of course, I guess we're well into the realm now that's called nanotechnology. We're doing nanotechnology from the top down rather than the bottom up. Doing it from the top down, at least for the electronics, we can continue to connect everything. The challenge of the people building single electron transistors and the like from the bottom up is how they put 1 billion of them together and make it into an interesting, useful function. It'll take a while to see how that's going to happen. For a more linear view, again, exponentials tend to distort how we look at things from a human point of view. If you just look at the qualitative progress over a period of time, taking an Intel 1978 technology and a modern technology, this is a 6-transistor static RAM cell compared with 1 contact opening in the 1978 technology. The continued evolution of these things over a period of time really have a qualitative effect, not just a quantitative one. I actually think we're breaking the laws of physics in some of this. We're printing 50 nanometer lines with 193 nanometer light. We're printing lines at 1/4 the wavelength of the light. This is something that I would have thought was impossible. And, if I go back to that other curve, I remember thinking that 1 micron was probably about as far as we were ever going to go, a couple of wavelengths of visible light. We wouldn't have a way around that problem because imaging really requires, it's hard to make images smaller than the wavelength of light. Then we moved to ultraviolet light, and I thought maybe 1/4 of a micron, maybe we'll get there, and that'll be about as far as we're going to go. And we blew through that. Now we're sub-10th micron, 90 nanometer technology in production quantities, and we're looking at printing lines 1/4 of the wavelength of the light. It really is amazing that we've been able to do that. Lasers are great for improving some of these capabilities. Of course, this requires that you use a low contrast optical image. Your contrast drops as you do this, but you use a very high contrast photoresist, and you can, with adequate controls, actually print these fine things. For those of you who haven't been in a fab recently, this is a sort of cutaway picture of what a modern step and scan production tool looks like. You know, a several $1 million tool using an excimer laser, and, a variety of things. It's a far cry from the original systems that Bob Noyce and Jay Lass put together at Fairchild to do our initial lithography. Well, we've been working hard on the X and Y dimensions. We haven't neglected the third dimension, the vertical one, either. The minimum insulator thickness has stayed also on a line that goes down exponentially. This one probably surprises me more than the line width did. I remember doing a back of the envelope calculation about the time Intel was formed back here, and convincing myself that statistically, if you went to layers that were less than about 1,000 angstroms, 100 nanometers thick, you'd probably get enough fluctuations that the things wouldn't be very good. But I didn't realize, or I should have, I guess, but the force was with us. Chemical forces really helped. And you don't get a statistical layer of atoms coming down when you oxidize the silicon. You get nice chemical reactions that really do maintain the integrity of a layer down to very, very narrow layers. Here we are, a couple of nanometers thick physically. Electrically, they look a few nanometers thicker than that because I guess the electrons can't get all the way to where we see the edges. And if you look with a transmission electron microscope at the silicon substrate, the insulator layer, and the polycrystalline silicon on top, you see these structures really are getting down to a few molecular layers thick. Well, see, you can't go much further than that, but you don't have to in this case. If we go to a material with a higher dielectric constant, we can actually get higher fields in the silicon with a thicker dielectric. This is an experimental structure, and the capacitance goes up something like 60%. But the great deal is the leakage current. Here you're getting down where you get a lot of tunneling. Leakage current decreases 100-fold. So there are things that can be done as we approach some of these limits that preserve our rate of evolution of the technology without getting off the trends we've been on historically. These have all led to dramatic increases in the performance of the electronics that we build. Here I plotted processor performance, and I'll excuse myself for using only Intel data, but that's the easiest for me to get my hands on. And you can see that over this time period, from the first microprocessor in 1971 to modern microprocessors, we've had about 5 or 6 orders of magnitude improvement in processing on an IC. That's a compound annual growth rate of about 50%, or a doubling in performance every 20 months or so. Those of you who have heard Moore's law quoted as doubling every 18 months. Notice I never said 18 months. I said 1 year and 2 years. One of my colleagues at Intel, Dave House, translated that into processor performance and decided that went a little faster than a number of components. So he was the guy that said 18 months, not me. But it's pretty close to what's happened on the processor performance over that period. And it shows really no sign of decelerating. In fact, if anything, over this part of the curve, it's accelerated. Now, we get some problems coming along here. One of them that I think is an important feature of this conference, and that is what is happening to the power. And here I'm looking at 2 contributors to the power: the active power of the processors, which are getting up to the power dissipation of a fairly bright light bulb, and power densities that we used to strive to get in power transistors. This is getting to be a problem. I don't want a kilowatt in my laptop. It would be very uncomfortable. From practical reasons, the power is going to have to roll off there. But the thing that is probably more disconcerting here is what is happening to the power contribution from leakage, not the active power of the device. That is a steep exponential. We've been fighting the power for quite a while, and our best tool for fighting power has been the power supply voltage. Here you get the square dependence on it. I suppose we can call this an exponential also, although it's kind of a stepwise exponential. We used to live with 12 volts, and we went to 5 volts. We were going to stay at 3 for a while, but we discovered that cutting the voltage was so nice for power, we just kept right on cutting the voltage. Now every new processor seems to pick an optimum voltage, and we continue to lower this principally to get the lower power. But of course, as we have much thinner dielectrics, they like lower voltage also. Now, again, this can't go on forever. You need at least a few hundred millivolts. I don't know exactly what, just to overcome some of the noise problems that will exist in digital devices. I suspect something around 1 volt is going to be a limit, but I sure have been wrong on a lot of these other things that I suspected were going to be limits. And you folks probably know that a lot better than I do. We chemists don't understand this kind of stuff so well, especially when we don't look at it closely anymore. But there are new things we can add that help with a lot of these problems. For example, moving from silicon to silicide gates helps considerably. We can continue to improve the performance of the transistor by purposely straining the silicon in the region. You strain it one way for the N-channel device and the other way for the P-channel device, and improve the performance of both transistors. As we look a little further down the road, we see things like a high dielectric constant gate dielectric, which gives us the higher electric fields while still keeping the leakage current down, and new transistor structures. One of which is the tri-gate structure I've shown here. This is an interesting device because it kind of changes, at least the way I've always thought of transistors, around completely. As we got to make very, very narrow line widths, down here in the 100 nanometer or less range, all of a sudden it doesn't make sense to deal with thin films in the other direction anymore. We just make a relatively thick film and make the transistor move in the other direction. Here the gate wraps completely around the silicon, which is sitting on a silicon insulator in this case. So you get a source and a drain and a gate that depletes the silicon from 3 sides. You can make a fully depleted transistor in this manner and cut the leakage current dramatically and get very high performance. It's the kind of thing that you don't think about till you get down to the dimensions where it suddenly becomes possible to build this kind of structure. This kind of a transistor might carry us significantly farther than we can go with only the techniques we've had available in the past. Of course, we have to be able to continue to print finer and finer lines. To do that, we need shorter wavelengths. We can't continue to print at a smaller and smaller fraction of the light we're using. But the technology generations that we're seeing, even by the regular scaling we've been doing, where we've reduced the line width by a factor of about 0.7 with every technology node we go through, from today's volume production, we can make conventional transistors down to the 30 nanometer range. It takes 2 or 3 years between generations. 3 years is the typical roadmap number that the SIA puts out, Semiconductor Industry Association. 2 years seems to be what we've been doing over the last few years and expect to be doing for the next few generations. So we're talking, 10 plus or minus 2 years of conventional scaling. Below 30 nanometers, it's not clear that the conventional devices will work, but something like that fin transistor I showed on the last slide looks like a very realistic possibility. To make these very narrow lines, though, we need a step in lithography. And this is a tough transition that we're going to have to go through. But we've been working on a technology using what is called extreme ultraviolet, EUV. This is a wavelength range. It used to be called soft X-rays, but X-rays got kind of a bad name in the industry, so the name was changed. But with the experimental system that currently exists, we can print 50 nanometer lines in spaces, small dots, and it's continued to be improved. It gets to be much more complicated optically. There are no materials that are transparent really in these ranges, so you can't use lenses. You can't use masks that you put the radiation through. Everything has to become reflective optics. Even air is an important absorber, so you have to work in a vacuum. Simple mirrors don't work. Instead of a metallic mirror, the mirrors you use here have something like 88 layered alternative of two materials to give you the high reflectivity that we need. Working with about 13 nanometer light, that's something less than a tenth of the 193 nanometer that's used in production now. And the industry has been investing in this kind of a system for quite a while. This is the prototype that exists in Sandia in Livermore. An industry consortium has been working with Sandia and with the Livermore National Laboratory to develop this to a useful technology. We're working with them because the EUV technology generally came out of the old Star Wars program. And it seemed most productive to continue with the group that had been working with the technology rather than starting all over someplace else. But as you see, this is a pretty complicated looking machine, and it's every bit as complicated as it looks. The mirrors have to be figured significantly better than the Hubble telescope, and then we have to be able to make them on a production basis. So it's a real challenge. But one thing it will do, it'll keep us on the exponential of the cost of a lithography tool. Well, as you see, a lot of things are changing exponentially. There's reason to believe that each of these has a problem. But I remember thinking $1 million machine was going to be prohibitively expensive for the industry. But we've blown through $10 million per lithography machine and are looking at things that are significantly beyond that. The secret is the productivity of the tools has increased at the same time that the cost has. Again, allowing us to continue to decrease the cost of a transistor to make cheaper and cheaper electronics. But we ought to remember that no exponential is forever. Your job is delaying forever. In the 40 years since the first commercial integrated circuits, or the 50 years since the first commercial transistor and the first ISSCC, I think we've built a fantastic industry. It is the most complex processing industry that I can identify by a significant margin. We manufacture the greatest number of items, if you take my item as a transistor rather than as the product we typically sell. Now, I don't think you can count bits on disks. They're not individually manufactured. They're just an area that happens to get polarized in a particular way. We've had million-fold, actually 10 million-fold cost reductions, and we've passed it on to the consumer. Again, something that no other industry I can identify has done. I discovered recently, or I was told by an economist, that the semiconductor industry has become the largest manufacturing industry in the US as measured by value added. Because we start with sand and a lot of value is added in there. And of course the electronics industry, taken worldwide, is the largest manufacturing industry that's there. But there's still a lot to do. And I think there's a lot of life left in the technology we've been developing, and there are a lot of clever ideas of how to extend it in some non-conventional ways. And its ability to infiltrate sort of everything society does is tremendous. It is really a ubiquitous technology and something that I think will continue to have a very important role for the foreseeable future and beyond what I can foresee, certainly. I am certainly honored to have been part of it. Thank you.